All right, hello everyone. We're going to be doing another video today on the astrodynamics of the interplanetary trajectory that we're talking about. Recap from last time, we have the three phases of our mission, astrodynamically speaking, where the first phase is leaving Earth, second phase is the half orbit around the sun, and the third phase is arriving at Mars and speeding up relative to the sun, slowing down relative to Mars to be caught in Mars orbit. Remember from last time that the first burn's delta V is equated with this formula. So a little bit on the theory of how we're able to solve for a mission that has orbits in three different reference frames. First being around the Earth, second being around the sun, and the third one being around Mars. The way this is done is through the patched conic approximation. As you know, each orbit, whether it's an ellipse, circle, hyperbola, what have you, around a reference body is a conic type of round shape. And what happens is if you look at the mission in terms of the sun, big overview of it like this, what happens when you leave Earth's sphere of influence, nothing changes. You go from technically being closer to the Earth and having the Earth be your central frame, but you can take the hyperbola when you're leaving Earth, the ellipse around the sun, and the hyperbola entering Mars, and from the perspective of your mission, draw them as one line. So you start off with the hyperbola in the Earth's reference frame, which without any input from the spacecraft, once you cross that boundary, becomes the ellipse around the sun. And again, when you hit Mars, becomes a hyperbola coming towards Mars. Part of that is something I mentioned, the sphere of influence, you're probably familiar with, but there's an imaginary line, circular orbit, somewhere at a distance from the body that we're talking about. For the purpose of our conversations, things within the sphere of influence are within that central body's reference frame. And that's why we have the hyperbolas when we're coming and going, even though around the sun it's an ellipse. We solve for the sphere of influence with gravitational parameter of the body we're talking about, divided by the gravitational parameter of the sun that body is rotating about, all to the 2/5 power times, and this says radius of the planet. What it means is radius of the planet's orbit around the sun. In the case of the Earth, using one astronomical unit as about 1.5 times 10 to the 8 kilometers, sphere of influence is about 924,000 kilometers. For context, the orbit of the moon around the Earth has an apogee of a little less than half that. Likewise, this is for Mars. The Martian sphere of influence ends about 400,000 kilometers above the surface of Mars. Now, how do we actually mathematically equate these different phases of the mission? We do so by saying the delta V1 that we're leaving is the same as the excess hyperbolic velocity. And that hyperbolic excess velocity is any number above zero of the spacecraft's speed when it hits the exact edge of the sphere of influence. And that's because to exactly escape, if you provide just enough juice to escape a planet's orbit, at the edge of the sphere of influence, you'll have a zero velocity. So anything above that is hyperbolic excess. Let's talk about the velocity right at that point. Now, using the vis viva equation, we can state that the energy throughout that hyperbolic orbit and throughout the mission after the burn happens, the first burn, is constant. So we can equate the two sides, noting that R infinity will just go out to infinity, so making that term zero. We can solve that after the burn, when we're going to leave Earth, our velocity at that low Earth orbit point becomes the square root of hyperbolic excess velocity squared plus 2 times the gravitational parameter of Earth divided by that initial orbit's radius. All right, and that's it. Thank you, guys.